Hello everyone and welcome back to my channel. I'm Mohan and let's get started with today's topic. Today we are going to talk about SHAPLY values, which are a great tool for local explanation. We'll also delve into what is the local explanation and why we should be caring about it. So let's go. SHAPLY value comes from a strong background of game theory where we want to know how if there are 5 features in a data and they are giving some certain output, let's say 1,000 points. So we want to know how much each feature has contributed for that output of 1,000 points. It's not likely that all the 5 features have contributed equal amount. So that's what Shapley values help us to understand. There is a very good library available on SHAP and you can install it because we are going to see how we can implement this library in the Jupyter notebook for our Tennessee Eastman data. But before that, we should know what is SHAPLY value and a little mathematical background behind it. So let's start. The SHAPLY value is very simple. It has basically 4 steps. First, we need to know what is expected value, which is nothing but just the mean of our target. I'll talk about it. Feature permutation, calculation of Shapley values, and finally the visualization of the feature importance. So let's see what is expected value or base value. Let's say we have a data set with only 2 features, x1 and x2. We put it in a black box model and we got the output y. So the expected value is expected value or EY is the value of target when we randomly choose the feature. So suppose I choose x1 and x2 randomly and I get, let's say, 10 values. I repeat that 10 times and I get 10 values of y. Then I average that value of y and I get the expected value. But in this case, I'm not in this particular example. For the sake of simplicity, whenever I say randomly chosen values, I'm just going to replace that with 0. But in the actual case of Shapley value, this whenever I replace things with 0, it will not replace it with 0. Rather, it will sample some random values from the dataset that it has seen before. Alright. So keeping that in mind, let's move ahead. So what is the local explanation? We'll understand that in the context of our use case, which is the Tennessee Eastman data. From the system, from the entire plant, we're continuously monitoring our sensor measurement. This is a sample of the sensor measurements. And let's say for this particular, the one that I have highlighted, we put it in from the black box, we got an output saying the predicted fault is fault number 20. But as soon as you get this result or the operator gets this result, the first question from him will be why and which feature are leading this black box model to predict this particular output. So that is what is called local explanation. In the previous videos, we have already seen what is global explanation, which gives a global idea of in our dataset which feature are important. But in this case, we want to know for this exact sample which feature have been contributing the most. All right. And to further investigate the SHAP value with a very simple example, I'm taking this data set with only 2 features and I have the corresponding y value. I put the x1 and x2 feature in the black box model, which can be anything starting from simple linear regression to complicated neural network. I don't care about that. As long as I have access to the input and output, I'm good. And the first, after we know what is expected value, the second step comes is feature permutation. What is feature permutation? Let's say I want to, well, this is the simple data set that I want to consider and I want to get Shapley value for this particular observation. But these are my feature and this is the output of my black box model. So I want to explain only this sample. So the first step we're going to do is feature permutation. For that, this is the sample that I want to explain. And then I'm going to permute it in different way. So what I'm going to do is for this is the first one is as it is. In the second case, I'm keeping the first variable constant and I'm randomly permuting the second variable. but in this case I'm just putting 0. Then I'm randomly permuting the first variable and keeping the second one constant, and in the final case I'm randomly permuting both the variables. After this permutation of feature, I'll put each of these samples into the neural network, and I get the corresponding output value. And then, in order to calculate the SHAPLY value for this sample, I'm going to use this table, this one and this one. So let's see how we can calculate SHAPLY value in the next step. Well, yeah. So as I am randomly permuting my both feature x1 and x2 here, this particular value is my expected value of y. Alright, this is my expected value that I was talking about in the first slide. Okay, because I'm randomly permuting x1 and x2, both the feature. So SHAPLY value estimation. We got this table of permuted feature and their corresponding output from the black box model. So for the first, we'll calculate the feature importance of x1 or the SHAPLY value of x1. For that, first what I will do, at first I'll calculate the feature importance or SHAPLY value of x1. I'll get the output of the black box model when both the features are intact. Here F represents this black box model. When both the features are present, and subtract the output from when first feature is not present. So this will give me an overall idea of how much first feature means to me. So if I see when x1, x2 is present, the output is 92, and when x1 is not present, only x2 is present, the output is 67. I just subtract these two and I get the value 28.45. But this is not the only possible scenario. The next scenario can be when I am only taking the first feature, like this case. So another scenario can be when I'm only taking the first feature and subtracting the output when I don't have any feature. That means this one. So 101 minus 67.67, I get my output 33.67. So after calculating this and this, there is no other possible combination can be estimated. So I can obtain the SHAPLY value of x1, which is nothing but just the mean of these two values. Alright, and that will be 31.0. The same thing I can repeat. The same thing I can repeat for the feature x2. First I'll calculate both features minus when feature x2 is not present. Then when feature only x2 is present minus no feature is present. And then I'm just going to sum them up. So from here we can see that x1 has a very positive impact, whereas x2 has a negative impact on my output. To visualize, we got this is our data set, this is our SHAPLY value, and our expected value of x is 67.67. This will be our base, and from that base we'll try to calculate how each feature is contributing. So for the SHAPLY value of x1, we see that it pushes the base value into plus 31.055, and the SHAPLY value of x2 pushes it leftwards because its value is negative, and finally we achieve our target, which is 96. Alright, so this is how we visualize the SHAPLY values. You can clearly see that x1 has a positive impact on our output and it has higher impact, whereas x2 has a negative impact and it has lesser impact compared to x1. I hope this explanation of SHAPLY value was clear. In this example, I'm taking a very naive case where in case of randomly permuting, I'm just putting 0. Once we are clear with this, now let's go to the Jupyter notebook and see how we can implement this on our Tennessee Eastman dataset. So here we are in VS Code, and first we import the necessary libraries, our necessary data files. I concatenate the fault-free and faulty data, which we have been doing a lot throughout this video series. Then I'm going to scale my data, standardize my data so that the feature won't have weird imbalances. And for the testing data, I'm just taking a sample of my entire data so that it won't be computationally very expensive for me, and I'm neglecting two different fault features. After that, I'm trying to I'm scaling my data, my X data, and then I'm adding a control feature that we saw in the last video so that we can know, because this control feature is just random numbers, we know that it do not have any predictive power, whichever feature in our dataset comes after this, that absolutely do not they do not contribute anything towards the output prediction. So that's why I'm adding a control feature, and this is my X modified, and this is my corresponding labels. Alright. After that, I'm doing my training test plate. This is my Y train shape. This is my X train shape. I have 53 feature, where 52 are my sensor values, and one is the randomly added control group that I added. Yeah, and we can see that we have almost similar distribution from each fault class that we have. So yeah, there is no class imbalance here. In the next step, we are going to train a XGBoost algorithm. For that, we are importing the XGBoost classification object. Then we are fitting it on our training data. In the training data, we have an accuracy of 97%, whereas in the test we have accuracy of 86%. So this is a case of overfitting, but we can work with that because 86 is pretty good accuracy. Next, I'm creating a data frame because this data frame will help me visualize the plots given by SHAPLY value in a better manner. For that, I'm making a data frame using just the test data and the feature name. So if you see the test data, it is just the feature. It's a data frame with feature name, and I also have the control feature at the end, which will help me see that what does my control feature stands, because any feature after the control feature will basically have no predictive power. Then I'm importing the SHAP library. We'll import SHAP, and then sharp.init.js. It will help us create nice plots. Then from the SHAPLY library, you import sharp.kernel explainer. You give it the trained model. It can be any model. That is also in the SHAP library, in the SHAP website or documentation. You can see how you can do it for neural network as well. All right, and then you give some background data. So this X-train. So I'm giving it a downsampled training data so that it can learn that how the data set looks like. From there it will sample. In the example when I told that it randomly permutes some sample, it randomly permutes those samples from this training data set. Okay. And I am choosing one index, let's say 56 index, and I'm only going to generate explanation for this sample. So what it says, it takes a lot of time because we saw that it does permutation for each feature, and here we have 53 feature. The time taken by this SHAP algorithm is exponential with respect to the number of feature. So when you have a lot of feature, this is not a good idea to do for every sample. Rather, for one sample you can do, and then yeah, then you can calculate the SHAPLY values for that particular sample from the test data. Okay, we got that, and now let's see. So what is the SHAPLY value looks like? It's a list of number of class. So here I have, let's say, 19 total, 18 or 19 classes. According to that, I have that number of list, and each list in here contains the corresponding feature importance of 53 variables. So if I do, yeah, now if I do sharp values and I take the first element of the list and do dot shape, then I see it has 53 uh, 53 elements, which represents the sharply value for individual feature, for each feature, and the 0 represents the for the fault's first class. For the first class of fault, it gives me sharply value for 53 features. All right, so now let's see. Now let's visualize this using the force plot. For that, I'm just creating this sample test data and sample test label from this particular sample, and yeah, so I'm using that in my XGBoost trained model. So the predicted class is 0, but the actual class is 3, and now I get the force plot for individual for each fault class. For fault class 0, we see it has pretty high positive value 0.43. For fault class 1, it's 0. For fault class 2, it's 0. For fault class 3, 0.43. See, there is between fault class 0 and fault class 3, there is very similarity, which we have seen throughout this video series, that fault class 0 and 3 are almost indistinguishable with naked eye even. So we can see this is logical. This gives us a logical reasoning that okay, there is a confusion between fault 0 and fault 3. Alright. Now let's see for other fault. All other type of fault we see it gives close to 0 result. Alright. And also the important thing is, let's see here. You see what each feature is contributing. These are the name of each feature, XMB9, XMB18. They're contributing positively for these samples uh, to become a fault class 0. And here if you see clearly, here it's written base value. The base value for this fault class is 0.005, and there is base value for all the fault classes. You can see the base value for this is 0.06, so on and so forth. Yeah, so most of the cases the base value is around 0.05, which is, if you don't have any feature or randomly select feature, the base value you will get is 0.05. And the SHAPLY, this plot gives us how each feature is contributing to deviate from this base value. So yeah, I think this is a pretty good explanation, but the problem is when you are using SHAPLY value, it's computationally very expensive, and it's gets even more computationally expensive as the number of features grows. So there is another method used when you can do it very easily, that is called tree explainer. So in the SHAP library also you can find this tree explainer, but the disadvantage is this tree explainer is not model agnostic. It can be only work for tree based algorithm like XGBoost, any kind of boosted trees, random forest, and decision trees. Alright, but this is extremely fast. You do not need to give a background sample. It just takes the splits of the tree in and creates the samples from there, and it's extremely fast. So in the previous case, I for a single sample it took me around 50 seconds, and for like 1000 sample it will take me less than 3 to 4 seconds. So yeah, so for 50 samples it took me 8 seconds because in the background my recording is also running. That's all. And if I see my test, yeah, this is just the test data. And then what I'm going to do is I'm going to create a similar plot, and here I have a predicted value is 10 and the actual value is 10. So let's go and see directly the 10th fault class. Yeah, so here we can see the 10th fault class is the highest value. This is basically the value of logit. The logit as I'm using a XGBoost algorithm, the XGBoost algorithm gives a logit value, and this then softmax activation is applied on this logit to finally obtain the the class label. So this is basically shows the logit values when you do the tree explainer. Okay, and you can see that what values are contributing for this particular the particular output of 5.3. Alright, and then you can also get a global idea using the SHAPLY method. It just combines throughout a lot of samples to give you a global idea. This gives you an idea, this plot. uh, so you see that this XMB10 has the highest feature importance, which was very similar in the random forest algorithm as well, if you do not remember. So this was my plot in the last video where I did permutation feature importance. Here also I can see the feature XMB10, XMEA21 are highest feature importance, and so as in the SHAPLY value. You can see XMB10, XMEA21, XMEA1, these have highest features. So that gives us a consistency that okay, for different features we are getting for different methods we are getting the same result. That means all these methods are valid and they can be implemented in practice. Well, that was it about this video. I hope you find values and you can go ahead and implement SHAPLY values in your use case. In the next video, we'll see another model agnostic method. So till then, see you.